All right, ladies and gentlemen, we're going to talk about the Hertzsprung-Russell diagram today. It's just a graph. It's a pretty crazy graph, but it can tell you a lot. It can tell you how hot a star is, how bright it is, how big it is, and if it's going to be around for a while or not. And so there's something called the main sequence we're going to spot, and then there's a couple of outliers. So all of this will make sense. It's a fairly simple graph. What you'll need to do is look for the red stars, write things like that down, like that has title and facts associated with the red star, and submit that for credit. So the Hertzsprung-Russell diagram, it's just a graph with stars on it. That's all that it is. So if you take a look here on the x-axis, you have your temperature in Kelvin. Don't worry about Kelvin. We'll describe that a little bit. But 0 means absolute 0, no movement. And then all the way up to 40,000 degrees. And then 1 means lumosity, right? That's how bright the star is. And 1 means one sun. So our sun has lumosity of 1. The higher up you go, the brighter you go. And the lower down you go, the dimmer it gets, right? And bigger circles mean bigger stars. Okay, so if we put these stars in order from hottest to coldest, what is the correct answer? Well, the correct answer is going to be our hottest is blue, right? And then white, and then yellow, and then red, all right? Because if you go across here, temperature goes down as you go along here, okay? Coldest, and that's the coldest on the bottom. Now, what about brightest to dimmest? Well, we would look at our y-axis for brightest is up here and dimmest is down here, okay? And it's, I should say brightest, so forgive me, blue, white, yellow, red, right? And then dimmest is what this should say. So all the way down throughout here, we have our dimmest stars right here. All the way up here are the brightest stars. So wait a minute, that seems like we have some sort of relationship. Let's see what we can do. Biggest to smallest. See, it says hottest again. The biggest, we can see it's going to be blue stars and then usually white stars and then yellow stars. Then we have teeny tiny red stars down here. Okay. And that's what we should notice, right? So there's something we just learned there. There's a trend, right? When it comes to stars, the bigger the star is, typically the brighter it is. So if it's a bigger star, it's going to be higher up on here. It's going to be brighter. If it's brighter, it's usually going to mean that it's hotter, right? And if it's dimmer, that is usually going to mean that it's colder. And then the hotter it is, usually the bigger it is, right? The brighter it is, the hotter it is. The hotter it is, the bigger it is. And the bigger it is, the brighter it is, right? So hot, big, and bright, and then cold, dim, and small. So what we call here is we're going to take a look at these outliers here. There's two outliers here. We have these red supergiants, right, and our white dwarfs here. So these are the two outliers we need to memorize, all right, because they don't follow the rules here, right? Red giants are big, right, and red supergiants are big, and they're really bright, but they should be hotter, but they're not. They're not hotter, right? So the color red for stars and orange and yellow, red especially is usually associated with the coldest, right? And blue is the hottest. So red means cold. Even though they're really big, they're really bright, but these guys are cold, so they're outliers. And then we also have white dwarfs here, right? These guys are hot, 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 but they're very small, so they're not very bright. Okay, so usually the smaller something is, the dimmer it is, right? So these are small and dim, but they're very, very, very hot. So we have our two outliers along here. And this strip in the middle, what is this strip? Well, we call this strip the main sequence. Now, remember, right, we have our life cycle here, stellar nebula, then we have our star, depending on how big the nebula is. A big nebula will have big stars, and they'll go through red giant, red supergiant. Red giants will turn into planetary nebulas, and then our white dwarfs, which are hot but very small and very dim. And then you get a supernova for these red supergiants, and they'll explode. And then, you get either a neutron star, or if it's big enough, you've got a black hole. Okay. Main sequence stars, any star that fuses hydrogen into helium. All right. Any star that's not a red giant, a red supergiant, or even a white dwarf. Right. So if we look here, the main sequence stars, big and small, all of these guys are turning hydrogen into helium, every single one. Okay. And that's just all stable stars in the stable stage of their life cycle, all of them there. All right. So what about these guys in the stellar life cycle. Small to medium-sized stars, well, if you remember, they'll turn into red giants, then a planetary nebula eventually, and they'll reveal a white dwarf. So let's see if we can see this, right? We have our sun, which would be a stable, small to medium-sized star, and eventually they'll turn into red giants, as you can see right here. And then when a planetary nebula occurs, they will reveal the white dwarf. So all of these guys will eventually turn into red giants and then fade into white dwarfs, right? Interesting. What about these supermassive stars? Well, remember, massive stars and supermassive stars will turn into red giants and then they'll explode. And they'll either turn into a neutron star if it's just a massive star. And then if they're big enough, they'll turn into a black hole instead, right? So we can see that here. We've got our white and blue stars are the biggest, the brightest, and the hottest, right? So if it's a massive star, it's either going to be white or blue. Eventually, it will turn into a red supergiant, but then it will explode, so we won't see this on our HR diagram anymore. One other important thing that we should know, right? You want to title this size and temperature, right? Red, red dwarfs, right? These are the smallest stars, the red ones. They have a low temperature, right? But they burn for billions of years because they're just burning at such a small temperature, right? But these supermassive blue stars, the biggest stars, have a really high temperature. So therefore, they only live for 40,000 years before they run out of all of their fuel. They're just burning through it so fast. And then they go into the red supergiant phase, right? So life expectancy. The hotter and bigger it is, the faster it burns out. So these guys are really big and bright, but they burn out real quick. And then cooler and smaller stars last longer. So the smallest stars are the coolest, and they burn through their fuel the slowest. So they last for quite a while, right? Sometimes I think it's billions of years, 13 billion possibly. We have our review slide here for you, but I hope this was an informative video for you.